Hello, everyone. Welcome to my channel. This is an educational channel where I cover different people who've spent their whole life working on stuff that is very valuable, but they never got any type of recognition. And so you probably have never heard of what they're doing, or you vaguely heard of it, or something to that effect. Today is video number 198 on the reciprocal system of theory, which was a theory of everything that was promulgated by Dewey B. Larson back in the 20th century. He died back in 1990, but he left a lot of books and articles behind. Spent about 60 years developing the reciprocal system, the last 30 of which he was writing books with a deductive approach. Once he came up with his fundamental postulates, then he began to deduce a theoretical universe, and then more or less compared his theoretical universe with the universe that the scientists had observed and measured, and to see how they would compare, how they would match up. Now, Mr. Larson's theory states that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy, it's made out of motion. Motion is the relationship between space and time. That sets up a generalized reciprocal relationship between space and time. That's why he calls it the reciprocal system. It's a lot based on a kind of a mirror images, and motion is basically a fraction or a relationship between time or space as the numerator and space or time as the denominator. And all of the really fundamental qualities of dynamics and mechanics are relationships between space and time. So you can get rid of the MKS system of units, and you can just plug in a time and space system of units. For example, speed. We know speed is time over space, or space over time. 10 miles, the bike is going 10 miles per hour. 10 miles of space in 1 hour of time. But if you invert that, you have a relationship between time over space. It took me 3 hours to move that thing 20 feet. That is energy. Energy is time over space. But you also have time and space in multiple dimensions, because as part of his postulates, he posits the idea of coordinate space and coordinate time. We understand coordinate space, x, y, z coordinates, 3 dimensions of space or time, or 3 dimensions of space. But Larson also posits 3 dimensions of time. He calls it coordinate time. That's something that is a foreign concept to legacy scientists, and comes into play in Larson's system when you're dealing with what he calls the cosmic sector. Now, there is also, as part of his fundamental postulates, what he calls clock time and clock space. Clock time we're familiar with. That is, time is always getting later and later and later and later. And we recognize that and have for a very long time. But then there is also clock space. Clock space is that things are always getting farther and farther and farther apart. There's a progression of space, or a flow of space. These clock aspects are both scalar motions. These are motions that have a magnitude, but they have no particular direction. And you would envision this by taking a balloon and putting a bunch of dots on it with a magic marker. When you blow up the balloon, all the dots are moving away from each other, but in no particular direction. You suck in the balloon, all the dots are moving toward each other, but in no particular direction. The farther apart they are, the faster they're moving away from each other or toward each other. And that is what Larson calls a scalar motion. And that is the progression of space. And that was actually observed by the Hubble telescope way back in the 1920s. All of the distant galaxies are moving away from each other. So that is clock time and clock space. The other aspect in his postulates of time and space is that they both come in discrete units. There is a minimum unit of space and a minimum unit of time. They are not continuous, they come in chunks. The chunks are very small, so you don't really see them. In the case of time, the chunk is so small that over 6 quadrillion of them fit into 1 second. And for space, I believe it is 20 million of them fit into 1 meter. And when you have exactly 1 unit of space in 1 unit of time, you have the speed of light. And so the speed of light represents a midpoint of the universe, or a null point. Larson at times calls it the natural reference system. You can think of it as the origin of the universe. There is a half of the universe that's moving faster than the speed of light, and half of the universe that's moving slower than the speed of light. This contradicts Einstein's dictum that that the speed of light is the maximum speed of the universe. This is true when you're talking about the material sector, which is the sector of the universe that's moving slower than the speed of light. But the opposite is true when you're referring to the cosmic universe, where everything is moving faster than the speed of light. The speed of light is actually the minimum speed of that universe. Now, we generally see these relationships in space. In the material sector, you have coordinate space and you have clock time. These are familiar to us. And these are what the scientists use for observation and measurement in the material sector. The cosmic sector is generally unknown to us and manifests mainly as things having to do with consciousness, the communication, the alphabet, perhaps. And in the cosmic sector, everything is moving faster than the speed of light. You have coordinate time and clock space. And these are unfamiliar concepts to us. But by the reciprocal postulate, we can extrapolate. So everything that we know about the material sector can be transferred over to the cosmic sector, with the caveat that we just have to invert the roles of space and time. And so we can understand everything about the cosmic sector just by extrapolating from the material sector. So this basically doubles our understanding of the universe right there from Larson's reciprocal postulate. Okay, now there's a million other things to say about that, but we are going through Larson's book called Nothing But Motion that he wrote in 1979. It's primarily on atomic physics. And we're in chapter 14, which is called Cosmic Elements. And, so this is looking at this cosmic sector. He had already gone through the material elements in an earlier chapter. The elements of the periodic table are combinations of motions. So an atom is basically a certain amount, an integer, a discrete units of two-dimensional primary rotations, two-dimensional secondary rotations, and one-dimensional, well, he calls them electric, but one-dimensional rotations. And so those are the three numbers, A, B, and C. He uses the notation just like A dash B dash C. Those are the three numbers that he uses to determine the elements. And now he's looking at the cosmic elements. And so you would think that all you have to do is reverse the roles of space and time. And that's true to a certain extent, but there are some other factors that come into play, such as observation. We observe from the material sector. We see space, but we do not see time. The only way we see time is how it affects space, and it affects space in a reciprocal manner. Again, the idea that I use is the white dwarf star. The white dwarf star is an explosion that goes beyond of a star that is going beyond the speed of light. When it goes beyond the speed of light, that explosion then occurs in time rather than in space. And we do not see time. We only see how it affects space. And so what we see is the reciprocal of an explosion in time. We see an implosion in space. And that is why white dwarf stars are tiny and super dense, is because they have exploded in time. And so when we observe across a boundary, there's also a certain amount that's lost in the translation. So we have to take these things into account in addition to the idea of inverting the space-time relationships when you cross over into the cosmic sector. Now, Larson is going over the some of the legacy science behind the cosmic elements, what they thought the cosmic elements are, and they believe that the cosmic ray primaries are atoms of ordinary material elements. So we're going to go over his list of the reasons why this is not true. So we'll start right here. In the absence of any known alternative, this amount of evidence has been sufficient to secure general acceptance of the conclusion that the primaries are atoms of ordinary material elements. When the issue as to its validity is raised, however, it must be when an alternative appears, it is clear that there are many counterindications in the empirical data. The most serious items are the following. 1. The speeds and energies of the primaries are too high to be compatible with production by ordinary physical processes. No known process or even a plausible speculative process based on conventional physics is able of producing energies that extend up to the vicinity of 10 to the 20 electron volts. As expressed in the Encyclopedia Britannica, quote, how to explain the acquisition of such energies is a disturbing physical and cosmological problem. 2. With the exception of some of the relatively low energy rays that are thought to originate in the sun, most of the primaries have energies in the range which indicates speeds in the neighborhood of the speed of light. Inasmuch as some decrease in speed has undoubtedly taken place before the observations, it is quite probable, on the basis of the observational evidence, that the rays originally entering the local environment were traveling at the full speed of light. This is another indication of an extraordinary origin. Number 3. While the distribution of elements deduced from the cosmic ray charges approximates the estimated distribution in the observed universe as a whole, there are some very significant differences. For example, the proportion of iron atoms in the cosmic rays is 50 times that in average matter. Lithium has been reported to be as much as 1,000 times as abundant. The cosmic rays, therefore, cannot be merely ordinary matter drawn from the common pool and accelerated to high speeds by some unknown process. They must have originated from some unusual kind of source. These anomalies in the charge spectrum of the cosmic rays are given little attention in current physical thought, probably because they have no known explanation. But the significance that such deviations from normal abundance would have, if confirmed, was clearly recognized at the time when the first indications of these deviations were observed. For instance, Hooper and Scharf made this comment, quote, "An excess of heavy nuclei would suggest the necessity of reconsidering our fundamental ideas on the origin of the primary radiation," end quote. Number 4, all of the major products of the primary rays have extremely short lifetimes. If they do not undergo collisions before this time has elapsed, they decay in flight to particles of lower mass and equal or longer lifetime. There is much available evidence to indicate that this is also true of the primaries. For example, in some of the observed events, a transient particle leaves the scene of the event in a continuation of the line of travel of the primary and carries the bulk of the original energy. The straightforward interpretation of such events is that they represent processes in which the primary decays to the transient particle and continues on its way. The existence of a substantial number of high-energy pions in the incoming stream of particles is another item of evidence pointing in the same direction, as similar but earlier decays of primaries will produce pions with very high energies. It has been estimated that as much as 15% of the incoming high-energy particles are pions. The conclusion that can logically be drawn from the observations is that the primaries of the same general nature, is that the primaries are of the same general nature as the known transient particles, and that the entire cosmic ray phenomenon is a single process taking place in a succession of decay events, a process in which an atom with some strange and unusual properties is converted first into other similar but less massive particles, and then finally into products that are compatible with the local environment. Okay, so those are Larson's 4 basic reasons why he suspects that the primaries are not simple material atoms. A pion is just one form of what they call mesons, and a meson is, in Larson's idea, is a cosmic atom, I believe. We will go on and figure this out. The considerations summarized in the foregoing paragraphs indicate that the current explanation of the nature of the primary cosmic rays is not correct. They point to the conclusion that these primaries are not atoms of material elements, as now believed, but atoms of a special kind which have characteristics similar to those of the transient particles, and are produced under some unusual conditions that lead to entry into the local frame of reference at the full speed of light. Since we now find from the theoretical development that there is a continuing inflow of cosmic atoms, which are atoms of a special kind that, according to the theory, enter our environment at the speed of light and are subject to rapid decay in the manner of the observed transient particles, the identity of the theoretical and observed phenomena is almost self-evident. An outstanding characteristic of the results obtained from the development of the consequences of the postulates of the reciprocal system of theory one that we have had occasion to mention several times in the preceding pages, is the way in which they resolve long-standing and seemingly extremely difficult questions in a surprisingly simple manner. Nowhere is this more evident than in the case of the cosmic rays, where the finding that these incoming particles are atoms from the high energy sector of the universe clears up the many previously intractable issues in this area with remarkable ease. The basic questions, what are the cosmic rays and where do they come from, are answered automatically by the theoretical discovery of a sector of the universe in which objects with the observed properties of the cosmic rays are indigenous. The particular properties that characterize the constituents of the cosmic rays and distinguish them from the constituents of aggregates of ordinary matter are naturally the ones that are the most difficult to explain on the basis of current theories which try to fit them into the material system of phenomena. But these explanations are practically obvious once the existence of the cosmic sector is recognized. Okay, we will proceed from there tomorrow and maybe review a little of that, but basically he's saying that these are cosmic elements and not material elements that are being labeled the cosmic rays. And I think in this chapter, in the next chapter, he will go over this process. All right. Well, thank you for tuning in. We will be going over this tomorrow. So stay tuned or tune in tomorrow. Don't get discouraged by the complexity. Just let it wash over you and listen to my videos over and over and you'll pick it up. All right. Have a great day.